So let's get back to it. We're happy to have Tom Sidney Kirkova here now to speak with us about practical property testing. Now, property testing is a topic that is most often addressed in an academic setting, so we look forward to hearing more about how it works in practice. Please welcome Sid to the stage.
Hi, everyone. You should hear me well. You should see my screen. Looks good. So I want to talk today about practical property testing, and I know this is usually looked at from an academic perspective, and I know that there are really good papers and you should probably go read them. But in this case, I just want to talk about how you would use this in practice at your company to build real value. I'm going to talk about a few things. I promise this is the only slide with a list, but I'm going to talk about what property testing is, what it is, why we do it, all the relevant internal workings, as few as possible, as few as I can get away with, but there are some things you need to know. And then how you really get started on your actual project with some property testing. I will talk about property combinators. You'll hear about them later. Some test suite combinators as well to build your test suites more easily. And then I'll go into a real world example where we property test a web service that has a database attached behind it. So a real integration test. And if we have some time left, then I'm going to show you a bit about how to dig deeper, write your own generators if that's ever necessary. It shouldn't be, but we'll get there. All right, so let's get started immediately. To define a property test, I'm going to show you an example of a unit test first. And I contrast these two just because of what I'm going to show you right now. Here we have a unit test that asserts that if you reverse a certain list twice, this list is 173, then it should be the same list as you started with. Now, in this case, we have an input-output example. And that's why I call it a unit test. So a unit test is just a piece of code that you run. And if it crashes, then we say the test fails. And if it doesn't crash, then we say the test passes. And then the assertions that you see here are just a fancy way to make the code crash. Now, the only difference between a property test and a unit test is that the property test has an argument. And this argument over here is what I'm talking about. So here I have an example of a property test which says that if you reverse any list twice, then it should be at the original list. And the list here is really the parameter that the test uses. And we say that a property test passes if for any argument that we pass in, it doesn't crash. And we say that it fails if for any one of them, it crashes. So it should, for the test to pass, all of the examples must pass. And then the obvious question is, where do we get these inputs, right? There are a few options. You can either try all of them, which is exhaustive property testing. That's not what I'll be talking about today. And because it's rather infeasible for larger input types, which is what you're usually dealing with. And then the normal way to do this, or let's say the regular way, the practical way to do this, is to pass in random data. So this should explain what property testing is. Now, why would you do this in the first place? Well, when you're writing unit tests, you have to come up with these examples. That's tedious, it's not fun, people don't like to do it. And with property testing, you basically get them for free because the generator will generate it for you. You also get smarter examples because the generators will come up with examples that you wouldn't have thought of. And in that case, you also test the edge cases of your function automatically because the generator will most likely automatically generate them. There are also some negative aspects to property testing, which is that you have to come up with the properties somehow. Same problem with unit testing, except that properties are usually a bit more difficult to come up with because they have to hold for any argument, and there are not necessarily some obvious properties for your code with an argument. And the other problem is that you have to know about what generators are and how shrinking works. Otherwise, you're going to run into some really weird and ugly to debug error messages. So as an example, here is a property test run with QuickCheck. And in this case, QuickCheck generates 100 random lists, checks that if you reverse the list twice, you should get the original list back. And you see this passed 100 test. Going on, I'm going to talk about the internal workings of the property testing a little bit, just as much as you need to know. The first thing I need to explain is what a generator is. The generator is the thing that's going to generate the arguments that we need. A generator takes two things. It takes a seed value, which is used to make sure that the randomness is deterministic. You need to make sure that this generator is deterministic via the seed. Otherwise, you don't have reproducible tests. The second thing it needs is a size parameter. And a size parameter is only necessary because some data types, it's not obvious how to generate them nicely without a size parameter. For example, lists. If you say, give me a random list, there is no indication of how large it would have to be, which means that it could be that you want an infinite list or a list with 1 million elements or an empty one. And the size parameter helps the generator to guide the generation a bit to make sure that that's, let's say, more or less doable. So for example, if you have a size parameter of 5, the generator might generate lists of size up to 5. So how to build the generators is something for later, but for now, this is a bit of how the generator works. Next thing you need to know about is shrinking. So if a property test fails and shrinking didn't exist, you might see something like this. I have a property here that says, or I assert that this property might hold. And I say, if you uppercase all characters in a string, then they all become uppercase. And the property test will fail and say, here is a counterexample of one of those strings that doesn't match this property. And it is definitely not obvious to me why this string fails the property. But if I now turn shrinking back on, and this is the motivation, you'll get something like this. And it'll say, well, here's a counterexample. And it turns out that when you have a failing test, usually the output is a bit difficult to comprehend. So we try to make it more simple. And we call that process shrinking. And when you have a more simple counterexample to your property, you'll probably be, it'll be easier to debug what the problem was. And in this case, it's now rather obvious. The character 1, if you uppercase that, it stays the character 1, but that character is not uppercase. So the property does not hold. So the way shrinking works is once the counterexample is found, the counterexample is then put through the shrinking function to give smaller versions, or let's say simpler versions, because they're not necessarily smaller, of the counterexample. The test is then rerun with the smaller version to make sure it's still a counterexample, and then it's shown or recursively shrunk. All right, so those are the inner workings you need to know about. Next up, how do you really get started with this thing? I recommend using HSpec, and here is an example of the way you could write that in HSpec. HSpec is something like domain-driven development. If you write Ruby, you might know RSpec. It's something similar. So you say, I describe that this is the function I'm going to be testing. I specify what it's supposed to be doing. And then I write my property right there. And now, in this case, I use for all valid, which just says, generate me a list, and then use that. Generate me a list from randomness, and then use it for your property test. This only works if you have a genValid instance for the input. This genValid instance gives you access to a generator called genValid right there. And that allows you to run a property, to create a property to test with random data gotten from genValid. A lot of the existing data types already have such an instance, but it's very likely that your data types don't if you've just written them. So the question is, how do you get such an instance? And it turns out that you can generate almost all of the code necessary to implement these instances, and that's also what the library does. So here are the 3 lines you need, and this is all of it. So this is not hidden implementations or something. You just declare that there is a validity instance, and this will figure out what is in a foobar, and then make sure that all the subparts have to be valid in order to say that the whole thing is valid. And then gen unchecked is an instance to say I can generate an arbitrary value of this thing without checking whether it's valid. And then gen valid is the instance that's automatically generated by making a generator that says, generate me an unchecked one, check if it's valid. If it's valid, let it through, otherwise try again. So this is how you get your instance for free. So you get your free shrinking, free generators, and all is good with the world because you can use for all valid and you don't have to think about shrinking or generators anymore in the best case scenario. It could be that some of the subparts of your foobar don't have an instance for gen unchecked, in which case this line will give you a compile error, not a runtime error. And in that case, you can just say, well, we don't need a gen unchecked instance if we can just generate the subparts via gen valid as well. In that case, you use these two lines where the implementation is implemented via genValid instead of via genUnchecked, and you get your shrinking and your generators for free again. So then you can write your property test just the way you want. And now I'm going to show you another example, but this time a integration test. Here it is. This is the most basic integration test I could come up with. Main is the main function of your program. And I'm saying when I give command line arguments args, which I generate from randomness, nothing's going to crash. Obviously, this is a bit of a dangerous test because it could do some writing, so you have to know that this is safe, but it's a nice example for an integration property test. To get started, it might not be obvious what kind of property tests you might want to write. So there are some standard ones that you definitely want to look into because they will give you a nice hint of what you might want to write. Here's the function that you will use for such a standard one. It's called should-be-valid. It's a bit like should-be, where it has two arguments that check if they're equal. Should-be-valid checks that a given argument is valid. So you can use it as follows in an integration test where you have a function that does some I/O and returns a thing. I can now say, well, this thing should be valid, and you might have some interesting validity constraints, but you might not, and it would still be useful because the validity, first of all, it makes sure that the thing doesn't contain any exceptions anywhere, but also if the code run a thing crashes, you will already notice. So this is a super basic test that makes sure nothing crashes while you're doing things. You might find yourself writing a lot of similar properties, and I'm going to show you an example of a case where that might be happening. Here we have two property tests that are basically the same, but they just test a different function. So I'm testing that greater than or equal to and less than or equal to, they're both reflexive, which means that if you greater than or equal to something to itself, it should always be true. And because Haskell has higher order functions, you can factor this out. And you can say, well, I want to have a combinator. This is called a property test combinator, where I can say, here's my Boolean relation, my binary relation. I want to turn that into a property test that will check if the binary relation is reflexive. And then you can rewrite your test like so. And now you have factored out the property test. When it comes to pure code, there is another neat property combinator that you might want to know about because it's mostly applicable as a property that you can probably test for almost all of your functions. And here it is. It's called produces valids on valids. And this will check that if you put something valid into your function, you get something valid out. It will also check that the function never crashes because valid means, among other things most likely, that there are no exceptions anywhere inside. So if I have a function called compute a thing, which takes some input and produces a thing, now I can say produces valids on valid on that thing, and I can get my property test for free that says this thing somehow makes sense, at least a little bit. Next up are test suite combinators. This is where you can have an entire test suite with more than one property generated for you entirely for free. One of the nice examples is a lens spec. So if I have a lens, they have to follow the lens laws. So I might as well use a test suite combinator to make sure that any of the lenses I have follow these laws. And indeed, you can write a function like this, where you just pass in a lens and you get a test suite as the output. That will look like this. And you can get your output looking like so. So all of the three lens laws are tested for you. You didn't have to write a generator, and at least now you know that your lens makes sense. So these are super, super, super cheap tests that you don't really have to think much about. You don't have to write much about it. Just point your functions into the certain combinators and you get your tests. Okay, next step. Practically, you have a web server, you have a database behind it. We want to make sure that this is tested as well. We might want to use property tests. How do we go about it? So the plan of attack is first we set up everything that's necessary up front for the things that can be set up front. Second, we set up everything that needs to be new for every test. So for example, an empty database. around every test. We run the tests, we tear everything down afterwards, or around every test as well. So suppose we have our web service and we can access it with something called a client environment. Then we will have to write a function like so. Here we turn there is something called a spec with. Spec with A is a test suite that can expect to be using an A. So a spec with client environment is a test suite that can expect to be using a client environment. We want to be able to turn such a test suite into a test suite that doesn't expect anything. And the way we do that is by annotating the test suite by saying, this is how we make such a client environment for each test. What I'm going to say is, first, we set up something beforehand that we're going to share across the tests. So use before all. One thing I want to share across the test is an HTTP connection manager. You can reuse those, so that's nice. And they're not necessarily cheap to create, so we might want to do that up front. And then around every test, we want to set up our application so that we can connect to it, provide the test with the client environment, and then tear everything down afterwards. So assuming, forgot about this part. We still have to explain how this with my app is implemented. And what we have to say is, given that we get this HTTP connection manager, how do we run a test that needs a client environment? So this function that is the first argument here is going to be the test that takes the client environment. And the second argument is the connection manager that we get from before all. It turns out that if you have a Y application that you can set up with setup my app, then you can give it to warp, which is the thing you probably use to run your Y application, and just say, this is going to be a test right now. I need a port somewhere. Just make sure it's empty, and then run this function within it. And we're going to run the test within it with a client environment that can take this connection manager, and the URL of the server is going to be local with a given port that we get from warp. And now that we have a way to run a test suite that can expect to use a client environment, let's have a look at what this test would look like. So suppose that our API has something called call my API, which takes an argument and produces a result in a client monad. And we can run this client monad with a client environment. Then we can expect to write a test that looks a bit like this. Looks a bit scary. I'm going to show you all the pieces in one by one. So this is actually what you would want to be writing. So you would want to say, I have some client environments somewhere, and I call my API twice with the same argument, and the result must be the same. This is called idempotence. So I'm testing the idempotence of this call my API function. This is what I would want to be writing. But the problem is, of course, this arg needs to be in scope, and this client environment needs to be in scope. So the first thing I want to show you how to get access to is the argument. We do that using a property test. So we just say generated from randomness using for all valid. And then this also contains the shrinking, of course, but that's separate. And the next thing we need to get access to is the client environment. And because of what we wrote previously, we can now assume that the test framework will give us access to it. So we just pull it out of the it and get a client environment. And now the type of this entire expression is test suite that needs to have access to client environment. And we need to turn that back into a test suite that doesn't. And we use this function that we wrote earlier with my server. By the way, you don't need to do this in a property test. This is also how you write an integration test that isn't a property test. And now you have your entire test for an entire property integration test for your API that tests if a certain endpoint is idempotent. So you can start using this for real projects. So it looks like I have a bit less than half of the time left. That's going to be perfect, because then I can finish some of the extras. All right, so let's talk about what you do if the default generators are not good enough for you. That could be, or you might want to write your own gen-valid instance. In that case, you'll need to know how to write a generator. There are some building blocks that you need to know about. There are these two functions and then two instances that you need to know about. The first function is called such that. It's something like a generator filter. So what happens here is you give it a generator and a predicate, and it will turn it into a generator that generates a value and then makes sure that this value satisfies the predicate. If it does, it lets it through. Otherwise, it tries again. And the second function that you need to know about is called elements. This will take any value from a given list and turn that into a generator by choosing a random value from that list. Next thing, so here's some examples. So here are two generators for characters. One is to generate a suit and the other one for a value. Looks like I forgot the 10 here, doesn't matter. So two generators. And now I can combine them using the two instances I told you about. The first one is called the applicative instance, so you can put generators together, smushing them without them having to know about each other. So here I have a generator for a card that has a suit and a value, for example. And it also has a monad instance, that's the second one you need to know about, where I can, for example, say, choose a length of a list between 1 and 10, and then generate 10 of those, or that number of those cards with the generator gen card. So those are really the building blocks of making a generator. But the way I'm doing this here, where I generate a list, where I specify the size beforehand, it's not really the right thing to do, because as the test runner, let's say the test operator, you might want to say on the command line, give me larger lists. And then this won't be able to do that because it doesn't listen to the size parameter. So there's one more thing you need to know about generating values using these generators and how to make them yourself, which is that you can access the size parameter. There are two building blocks for that as well. The first one is called sized, which lets you use the size parameter that's being passed in. And the second one is called resize, which lets you reset the size parameter. And for a really contrived example, I say here, set the size parameter to 15, and then use the size parameter, call it n, and then generate n valid integers. So if you just left off this part, then the operator could set the size parameter by themselves. All right, so those are the building blocks of generators. Keep in mind that you can probably generate your generators automatically or have GHC do it, I mean. But given that you have written some of your own generators, now we can use them. So let's say you wrote one called my custom generator. You can use it with for all, which takes a generator and a property and then runs the property. Problem with this is, by default, when you use a custom generator, the shrinking is turned off. You'll see in a moment why that's the case. So if you do have an own custom shrinking function, my shrink, for example, then you can specify that your test has to use that shrinking function. And this is the way you do it. You use for all shrink. Right. The last part of the talk is just some dangers, some things you're going to run into when writing your own generators that are going to potentially lose you some time. This is one of the most annoying things that I have spent a lot of time on that I wish I didn't. It's called, it's a problem with shrinking, where if you use the default shrinker with a custom generator, things can go wrong. Here we have a custom generator called genValid such that greater than 5. What that does is it generates numbers greater than 5. But I test the following property using the default shrinker. And the property I assert, or I might think might hold, is any number greater than 5 is even. And you will know that this doesn't hold, but what's going to happen here is that QuickCheck is going to give you this error message. It's going to say, wait, there is a number greater than 5 that is not even, namely 0. And that does not make sense at all. And the reason why this happens is that what actually happened is QuickCheck generated a 7. It saw that 7 is greater than 5, okay, but it's not even, so the test fails. And then the shrinking starts, and the first thing that QuickCheck shrinks to, because it's the smallest value, is 0, or not the smallest, but the closest to 0, the simplest. And then 0 is checked, 0 is not greater than 5, so the test still fails, so it's a simpler counterexample, so we're going to show that to the user. So the thing to take away from this is that you need to maintain the invariance of your generator while shrinking. So you need to filter the result of the shrinker with a predicate greater than 5 as well. The next danger I need to tell you about is something about performance. This is about performance of your test suite. Usually when your property test suites are slow, it's not because your code is slow, but because your generator is slow. And here's an example to show you how that happens. These are two equivalent generators, so they will always generate the same values, but one does it fast and the other one does it slowly. The first one says, use no randomness and produce it 100. The second one says, get any integer and then check that it's 100, and if it's 100, then let it through. Obviously, the second one is going to be super slow. So you have to watch out for predicates that are rarely satisfied. This was an example. Or for expensive predicates. So for example, primality testing. The next danger is if your test passing depends on the size parameter, you have to watch out as well. Here's a nice example of that. I'm asserting that there is this property that any list is shorter than 100 elements. And quick check will say, yeah, seems right. Because the default maximum size is 30. So quick check will never generate values greater than, or lists greater than 30, which means this test passes. And indeed, if I say, give it a bigger size parameter, then the test fails. So watch out for properties that depend on the size parameter. And there's one more danger I want to warn you about, which is if you write your custom generator, you have to watch out with the sizes if your data type that you're generating is recursive. Here I have a tree data type with no values, just a tree, just some branches and some leaves, so just a structure. If I have the stupid way of implementing the generator, I'm saying either generate a leaf or generate a branch with 2 more trees below. If I'm going to look at the output, the sizes of the generated values, here I've done that, you'll see that they range wildly. So much more than from 1 to 30, which was what you would expect. So you have to watch out for generators that use the size in a nonlinear fashion. So the correct way of writing this, for example, is to say, give me the size parameter. If it's 1, generate a leaf. Otherwise, split the size parameter into 2 numbers that sum to the size parameter. And then generate 2 subtrees with the 2 pieces, the 2 smaller sizes. So this is the last danger I wanted to warn you about. This is the end of the talk as well, so I'm going to show you some links to relevant projects. If you have any questions, be sure to ask me them, because I love helping people with property testing. So here are some of the links. First is QuickCheck, which is the property testing framework that's being used. That's also where the generators come from. The second is HVEC, which is the tests framework that I use. I like this one. I cannot recommend any of the others. And the third is called Validity, which is where the free shrinking, the free generators, the property combinators, and the test suite combinators come from. This also has different generators in QuickCheck on purpose, because the QuickCheck ones are pretty stupid sometimes, and the Validity ones really make sure that your code really works, because it generates much better edge cases. Good, that was the end of the talk. So I'm a bit early, it seems, because I just got my 10-minute warning. If there is anything else I need to do, Chris and Allison, now is the time to jump on.
We might have time. We might have time here for a couple quick questions.
Yeah, go for it.
Mihal asks, do your free generators terminate for types that have a majority of recursive constructors, or do they just loop forever and eat memory?
I might have to check my implementation. In that case, you may have, if it's a recursive type, you will probably want to write your own generators. It could be fixed, but it would be fixed in a way that's non-ideal in other ways. So I don't think I have. So no, if you have recursive types, write your own generator.
Okay, and Mihal also asks, while clever testing of databases, does it use free monads or explicitly connect to database instance?
This is just a real integration test. So this doesn't use any free monads. This is just in I/O, which is also what I recommend. You want to be testing your real code in a real scenario, not some pretend code.
Okay, great. So if there's further questions, let's take those to the session portion. But thank you, Sid. It's really nice to see property testing in a practical setting. The next session is going to begin in about a little bit, 5 to 10 minutes at 10 before the hour, so more like 10 minutes. And until then, you can find Sid spending a few minutes answering questions in sessions, and I hope you join him there. Otherwise, we'll see you back here at 10 of the hour.